Hello and welcome to this EERI briefing on April 25, 2015 Nepal Earthquake and Aftershocks. My name is Hemant Kaushik and I will be discussing part 1 of this presentation on building performance. Basically, I will be discussing different building typologies in Nepal and I will be concentrating on damages observed in RC frame buildings with masonry infill and wood frame buildings. This is the fourth presentation in a series of 14 presentations prepared in this briefing series. There are three common building typologies that we observed in damaged areas in Nepal. The three photographs here, they show the three types of buildings. Most common type of building are RC frames with masonry infills, followed by unreinforced masonry bearing wall buildings and wood frame buildings. We'll start our discussion on RC frame buildings with masonry infill walls. Such type of buildings are concentrated in urban areas and district headquarters, and they are seldom found in rural areas. They are low-rise, medium-rise, high-rise. Interestingly, most of the private buildings are non-engineered. And we observed following serious issues in these types of buildings. First is they have poor geometry configuration. The non-seismic detailing is almost everywhere. The workmanship is quite improper. Generally, geotechnical investigation is not carried out and therefore the foundations are constructed on slopes and these are inadequate. So therefore we observed variety of damages ranging from minor to moderate to severe, even collapses, depending on location and details of these buildings. Here are three photographs that show three different rise buildings. So low rise, medium rise and high rise. So Chautara 3-story building, it collapsed. In Balaju, a 6-story building, it completely leaned on one side, and in Dapasi, a 17-story building suffered extensive damages. Now, interestingly, most damage occurred to those buildings which are sitting on the roof ridge tops, and this is most likely due to ridge top shatter amplification effects. Another interesting point is the infill walls in tilted buildings were less damaged. We can even find completely intact walls in many cases, like it is visible in all three buildings. There are large overhangs in almost all buildings in Nepal. Such progressive increase in floor areas in upper stories is done by extending beams and walls beyond the column grid lines. So the figure on the left has overhangs on both the directions, figure on the right has overhangs in just one direction. Such overhangs create a severe discontinuity in lateral load transfer path. Many buildings in Nepal have trapezoidal plan, and interestingly, at one end of these buildings, the ground floor is practically only a column, and then the upper floors have about 1.5 meter wide overhang. And as we move along the length of the building, the other end of the building is about 6 to 8 meter wide. Length of the building is around 15 to 18 meters. So this is serious geometric irregularity. And the floating columns are also very common. These are the columns without foundation, the figure on the bottom left. They create discontinuity in lateral load transfer path. Soft stories are quite common. For example, in this building in local Thani, there is a drastic reduction in lateral stiffness at the intermediate story level. Non-seismic detailing is found almost in all buildings that were damaged. The collapse of this 4-story building in Irko was primarily due to poor design and detailing, the non-seismic design and detailing. The figures on right, they show the zoom view of the damaged areas in this building. Another collapse of a 3-story building in Chautara was due to poor design and detailing. Here again, the masonry infill walls were not damaged, but the whole building tilted. This building was constructed on a downslope. The right figures, they show the zoom view of the damaged areas in the columns. The workmanship in RC buildings with infill walls is extremely poor. What we observed is the column caps that is constructed along with the upper slab is not properly constructed. The concrete quality in the beams and in these column caps is very poor. There is no proper connections between two perpendicular walls, masonry infill walls. There is no reinforced concrete lintel over the window openings. There is no proper foundation to the walls below the plinth level. So all these things, they basically aggravated the damage observed in these buildings. The foundations are generally very inappropriate, and that is because of the reason that the geotechnical investigation is not carried out. These foundations are mostly the isolated footings on slopes, and failure of these foundations resulted in collapse or tilting of large number of buildings, like it is observed here in 3 buildings in different areas. We carried out a very interesting survey in Chautara, where we surveyed about 150 buildings on a street, and we found that about 49% of the buildings on upslope or flat ground and 60% buildings on downslope damaged. So basically it's the buildings on the slopes that have damaged more. More details about this survey will be provided by Brett Lizendia in part 2 of the presentation. So if we categorize damage in RC frame with masonry infills, we can say that there are pancake-type collapses, there are beam column joint failures, the shear failure of columns due to short column effects, rupture of column reinforcement because of inadequate design and detailing. We'll discuss about this issue later. Because of ground cracks, because of pounding of buildings, and in plane and out of plane failure of masonry infills. So these are different damage or failure observed in these buildings. Here 3 different buildings are shown which showed the pancake-type collapses. These types of damage or collapses because of non-seismic design and detailing, because of poor geometric configuration, gives rise to extremely weak columns, and therefore they can't undergo the large ductility demands that are expected during large earthquakes, and they collapse. Beam column joint failure was observed in many buildings because of poor connection detailing, because of insufficient anchorage and insufficient support to lintels. The figure on the left is a unseating of a reinforced concrete lintel from its position due to insufficient support. Then the figures on the right, they show poor connection detailing in beam column joints and therefore severe damage to this region. The short column effects are observed in the columns near the door and window openings. Now this is very common in case of school buildings where you have large window and door openings, and this actually is responsible for creation of the short columns. A typical column section is shown here. Buckling and rupture of column steel was observed in almost all buildings that were damaged, and this is because of a general practice that owners they follow. We'll discuss about this general practice in the next slide, but the figure here they shows the rupture of column rebar in a 3-story building in Chautara, the left figure, and the buckling of column rebar in a 4-story building. The figure on the top, it shows reinforcement detailing in a 5-story building under construction. It's quite clearly visible that the design and detailing is quite inadequate. Now this is the general practice that people follow. The column size is about 230 by 230 mm, and they provide about 4 bars of 12 to 16 mm diameter as longitudinal steel, with only 6 mm diameter bars about 200 mm center to center as shear reinforcement, and with 90-degree hooks. Now there are 2 mandatory rules of thumb in Nepal for RC frames with masonry infills and for RC frames without masonry infills. Though these mandatory rules of thumb, they allow such column dimensions and longitudinal reinforcement, but the minimum steel requirement in critical regions of columns is 8 mm diameter bars above 75 to 100 mm center to center and with 135-degree hooks. So clearly, the mandatory rules of thumbs are not being followed, and therefore the sheer failure of columns and buckling of longitudinal reinforcement was observed in many buildings. John Bevington will provide more details about these issues in his presentation on building codes. Severe ground cracks and settlement was observed during this Nepal earthquake and aftershocks, and these were responsible for foundation failures in many buildings. Here is a Arnico highway, Lokanthali, along with where we found ground cracks at several locations. And these are the tilting of the buildings along this road. Then because of the haphazard construction, unplanned construction, the buildings are constructed quite close to each other. This is responsible for pounding of buildings. So although the building has performed quite well, but because of failure of the adjacent building or because of pounding between these two buildings, the otherwise undamaged buildings suffered huge damages. For example, several buildings in Chautara suffered severe damages due to pounding. Now, in-plane and out-of-plane failure of masonry infill walls is quite common during strong earthquakes. This is visible in the 17-story apartment buildings as well as a school building in Sanko. Now, wood frame buildings are basically the post and beams, and they are constructed up to 3-story. The flooring is usually constructed using timber, and the roofing is CGI sheets. Now, 3 different types of infill walls are provided in these buildings: wooden planks, CGI sheets, and bamboo with mud. The 3 figures show these 3 different types of infill walls. In these buildings, the damage was observed due to slope failure and large ground movements. Cracking and collapse of the brick veneer on the building exterior was also responsible for severe damage to these buildings. Finally, the failure of foundation posts and roof studs were also observed. So, in summary, we found that most of the non-engineered buildings performed extremely poorly during these earthquakes, and this is quite expected. The foundations on slope performed poorly because of no geotechnical investigation reports. Severe geometric irregularities in buildings make them seismically vulnerable and they suffer more damages. Poor material and poor quality control resulted in more damage. Clearly, the seismic codes are not followed in such seismically prone regions. The non-seismic detailing was observed in most of the buildings. Unplanned development has resulted in haphazard construction, and which is obviously more vulnerable to pounding. The mandatory rules of thumb NBC 201 and NBC 205, they were published in 1994. They are not followed, and therefore the detailing in the members is quite poor. Now, new version of these codes are in the draft stage, and the requirements in these new versions are more stringent. The wood frame buildings were damaged mostly due to slope failure and large ground movements, and cracking and collapse of the brick veneer on the building exterior. More information about these earthquakes, more reports, data, photographs are available on EERI's Virtual Clearinghouse website. You can get geolocated data maps, photos, team reports from other teams as well as organizations, curated topic boards. I want to thank my virtual team collaborator Sabina Surana, who uploaded all my photographs to EERI map. I wish to thank following individuals and organizations who supported my efforts: EERI, Learning from Earthquakes Program, NSET, other team members, Professor Muske, Professor Tiwari of Tribhuvan University for helpful discussion on building typologies, my parent organization IIT Guwahati for allowing me to undertake the work, my doctoral student Bunisha Bora who assisted me in this presentation, Kishore Jaiswal for assisting with the wood frame slides, and last but not the least, Brett Lizindia for reviewing the presentation and for providing helpful comments. Thank you.